Today's lesson is about forces. We're going to talk about how forces act upon materials. It's quite important to understand because it allows us to make a decent choice for materials relating to the different stresses they're put under in their day-to-day use. Obviously, we would set up today's lesson to do some kind of starter task or put titles and stuff. We're not going to bother to do that today. We're going to just simply have a look at the content and what's going and then answer the questions. But the question here is, what would happen if you made a road surface from jelly? It wouldn't work properly because it just wouldn't react in the right way to the cars that go over it. And what the designers have to think about. Our aims and objectives today are just to do those things. I'm not going to read them. Here we go. So what are forces? Now we talk about forces as something that causes an object to change its motion, whether it's already in motion and it stops, or whether it's not in motion and it starts to move. So obviously my ball there is being kicked, so therefore that is a force being put onto that ball. When you go bungee jumping and you jump off, gravity is the force that pulls you towards the ground. And then obviously if you've got a ball that you're throwing, that will then bounce against the wall. But as that changes direction, we have 5 main forces that we talk about in DT. We talk about them in a slightly different way than we do to science. We focus on how the forces are felt by an object or a product that we would design. So here are the main 5. If you can have a guess what they might be. Top one, we have some kind of pulling motion, and we have some kind of squeezing together motion. We have something that is sort of pushed in one direction and pushed in another direction. The answers, if you haven't got them, are tension, compression, bending, torsion, and shearing. Now, on your worksheet, I'm going to ask you to define those, try and put it into your own words. If you can't do that, then here are your definitions. Now, here are real world examples. You can't realistically apply theory to real world examples unless you actually say what they are. So here we go. So here, what I'd like to do just on the slide, just having a look and using your brain, which of these pictures represents which one of these forces? So have a quick look at those, have a look through it, and then you should be able to see which one's which. Obviously, certain things might have multiple forces applied to them, but you should be able to guess them. The next point is to say, do multiple forces act on a product at once? Yes, they do. Any complex product will have more than one component, and that all those components will be put under different types of force and stress as they are used. So we're going to take the example of a skateboard. The interaction of those forces exerted on the parts require calculation. Here's our example. So we need to know what the parts of the skateboard are called so we can talk about them properly. So we look at the parts, think about how skateboards are used. We have a skater that stands on top. We have the wheels that go round. We have backwards and forwards. We have where we do kick flips and things where you twist, that you kind of push your feet against the board. So there's all sorts of forces happening here. So a couple of examples now, just to put it into context for when you have to do your work. So here's one that's not very obvious. So if you look at the axle where the wheel goes through, you saw on the other diagram that that axle would actually be static. It wouldn't actually move. So what happens is the wheels are on a bearing which spins round. But as the skater stands on top of the skateboard, it's pushing downwards on that axle, but the wheel is holding it still. Now it's not bending because the force is just from 2 points. That is actually a shearing force. And obviously, as the skater moves forwards, that force is trying to push the axle in one direction, but the trucks are holding it still. So as that happens, that axle is being put under a shearing force. And that is how that works. And that's how I would write that example on there. The next example, which is more obvious, is when the skater stands on top of the deck. As the wheels are on the ground, but the board is suspended above them, if the skater stands in the middle of the board, that board will then be that's being bent or bending. A bending force is being applied because it needs to not break as that weight is put on top. Now, lots of different forces happen to those skateboards when you do tricks, when you're moving. When you push on the grip tape, all sorts of different things. And what I want you to do with that task is to look at trying to work out what those forces might be and explain what you mean. One final point on this relating to forces is there's quite a big definition between forces that move and don't move. So not all forces are the same. So you look at the example, you've got a climber on the left hand side who is resting on his rope. He's taking a break from his climb and he's resting, putting his weight onto his rope. The climber on the right is falling. Now as he falls, that rope will catch him, but the guy on the left is a static force. It's a steady force applied to the product. So this rope, for example, if this climber is 80 kilos and this rope takes 80 kilos, if he's just resting on it gently and just resting, and that's taking his whole 80 kilograms, that would be fine. So theoretically that would work, that wouldn't break. However, with the dynamic force, that climber is accelerating towards the ground, and as that rope takes in the slack, and he falls and that rope finally takes in his weight, that weight will be much greater because of the fact that he's moving. So that's what we call a dynamic force. So therefore that rope would need to be rated much higher, to maybe even 160 kilograms, to take the moving or falling 80 kilogram climb. Okay, so static and dynamic. Here's just to explain it a little bit more. If you jumped onto an icy pond and jump up and down, or you step gently onto an icy pond and stand still, which one of those is static and which one is dynamic? It can be calculated as force equals mass times acceleration. So you take your mass and multiply it by the acceleration that you have towards the object, or on the actual object itself, and that is the force that you're applying. So which one of these, 1 or 2, is more likely to break the ice? Obviously, if you jump onto the ice, it's more likely because you are a dynamic load and you are multiplying your mass by the acceleration that you're taking.